Let G1 be a abelian group of order 6 and G2 is S3 for j equal to 1 to Pj with the statement Gj has a unique subgroup of order 2. Now explore this statement, otherwise you can get confused. So what is this? Pj, value of j is 1 and 2, so P1 means Pj, so we can find P1 as G1 has a unique subgroup of order 2, and similarly P2 statement is G2 has a unique subgroup of order 2. So P1 and P2 statement are about subgroup of order 2. So what are the possibilities of given options? Both P1 and P2 holds, neither P1 nor P2 holds. Option C is P1 holds but not P2, and option D is P2 holds but not P1. So first we recall some concept related to this problem. So fact 1 is, if order of G can be written as product of prime where P and Q are prime, with the condition that P is less than Q and P divides Q minus 1, means 1 less, then there exist then not there exist then either G is cyclic, G is cyclic or non-abelian. Statement or fact 2 is, if G is cyclic, if G is cyclic, then for every divisor, for every divisor D which divides order of G, then there exists a unique subgroup of order D. Subgroup of order D. This is fact 2. And third fact is, you have to focus on my words, not what I am written here, because something I can skip. So because of I am not able to write faster. Statement 3 or fact 3 is Lagrange theorem, which says order of subgroup divide order of G. And fact 4 is, if G is finite abelian group, if G is finite and abelian, then a positive integer k divides order of G, then a positive integer k which divides order of G, then G contains a subgroup of order k. G contains a subgroup of order k, means if 2 is dividing order of G, suppose 6, then there exists a subgroup of order 2. This is fact 4. And we normally know that a group of prime order is cyclic and cyclic groups are abelian. You can recall this, it may be used or may not be used. And fact 5 is, transposition transposition are self inverse. So these are few facts related to this problem. Now come to the problem. G1 is an abelian group of order 6 and G2 is S3, means symmetric group of 3 symbols. So use this fact to solve this problem. First order of G1 is 6 and we can write 6 as 2 into 3. So consider this is P and this is Q as fact 1. 2 divides so order of G, 2 divides so order of G, and 2 divides Q minus 1 means 3 minus 1. Then 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 G is cyclic. It means either G is cyclic or non-abelian. Non-abelian. It is said with the help of fact 1. Now, but G is given, G1 is given abelian. It is given. So now consider these two conditions. If it is abelian, then what we have means J is cyclic. Otherwise, J will be non-abelian. So G1 must be cyclic, and we know the concept of or fact 2. Use fact 2 here. If J is cyclic, then for every divisor D which divides the order of G, there exists a unique subgroup of order D. Means 2 is dividing order of G, and it's always it here it is also Q minus 1 condition is satisfied. So G has a subgroup of order 2, means order of H. Suppose H is subgroup of G and order of H is 2. So P1 statement which is saying that P1 has a subgroup of order 2 is true statement. Now come to this statement 2, as G2 is S3, and what is S3? It contains identity and transposition. Transposition are two cycles, two length cycles. So this is identity 1 comma 2, 1 3, 2 3, and 1 2 3, and 1 3 2. These are elements of S3, means order of S3 is 6. 1 2 3 4 5 6. Order of S3 is 6. Now we have to find subgroup of order 2. So possible subgroup of S3, or you can say G2, are, if we can form subgroup only contain identity and self inverse element, then it will be a subgroup. So identity and one transposition, suppose this is a subgroup, so call H1. H2 is identity and one transposition as 1 3. Now H3 is identity and other transposition as 2 3. So these are three subgroups. Normally we have three subgroups. So condition or statement P2 is saying that G2 has subgroup of order 2, and it is unique, but here we can find three subgroups of G2. So G2 has three subgroups, not unique subgroups. So statement 2 is not hold here. So only statement P1 is true, means holds, but P not, P2 not. So option C is correct. P1 holds but not P2. G be the group of all symmetries of the square, then the number of conjugate classes in G is. So to solve this problem, we will use a direct factor or rule. The number of conjugate class in D to N is given by N plus 6 divided by 2. So for d2n to 2 into 4 because of symmetries of a square. The number of conjugate class will be n is 4, so 4 plus 6 divided by 2, this one equal to 5. So which one option is giving 5? Option B is correct. So use this formula as a direct result and you can easily find the number of conjugate classes of the symmetries of number of non-isomorphic abelian groups of order 24 is. This problem can be asked in other way. The number of abelian group up to isomorphism of order 24 is. To find number of non-isomorphic abelian group, we use partition of some number. So how to use partition of some number? As order of group is given as order of G is 24, and we can write 24 as 8 into 3 means 2 raised to the power 3 into 3 raised to the power 1. Then number of non-isomorphic abelian group abelian group is given by P1 into P3, where Pn is the partition of n. So partition of 1 is 1 and partition of 3 is 3. So 1 into 3 is 3. So 3 will be the answer, means 3 non-isomorphic abelian group exist for group of order 24. So in general, we can write as, if any order of the group can be written as P1, N1, P2, N2, and so on, then we have to write partition of powers of prime. So partition, you can write it, this is small p, which are used in prime factorization, and capital P for partition. So partition of n1 into partition of n2 and so on, as we used this concept in above one. So answer is, consider the group homomorphism phi from M to R to R given by phi A is equal to trace A. The kernel of phi is isomorphic to which of the following groups? Here are some groups and we have to check that phi is isomorphic to which one. So we know the dimension of R cube, R2 and GL2R. So how to check isomorphic kernel of phi is isomorphic to which one group? As we know that isomorphic groups have same dimension, then we can easily check its dimension. As phi is given from M to R, means all 2 by 2 matrices, and entries are real entries from to R, and structure of phi is as trace of A. So kernel of phi is a set or is a group and can be defined as elements of this one will be all 2 by 2 matrices which are coming from M to R, such that trace of A is 0. This will be kernel phi. Trace of A is 0 and matrix A size is 2 by 2 and trace A is 0. It means that diagonal elements, so structure of A will be A minus A, B, C. This is the structure of A, and this is 2 by 2 matrices such that trace of A is 0. We define A as this. So dimension of this matrix A is 3. We can check how many independent entries coming from real numbers. So if we choose A, then minus A, we can easily put a negative of that. So first independent entry and second independent, and this is third one. So there are three independent entries. So dimension of A is 3. It means dimension of kernel phi is 3. So which one given group has dimension 3? If it is isomorphic, then its dimension will be same. So we know that R3 has 3 dimension because of R3, dimension of R3 over R is 3. So option C is correct. Of elements of order 15 in the additive group Z60 cross Z50. How to find order of an element in Zm cross Zn? It can be easily find out LCM of an element which is coming from Zm. Suppose this is coming from Zm, and order of another element B, and this is coming from Zn. So actually we are seeking those elements having their orders form LCM as a 15. So how we can 15 as LCM? Whenever order of elements will be 5 comma 3, LCM can be 15 comma 1, and LCM can be 15 comma 5. So these are the possibilities of orders of an element, and we can form 15 as a LCM. So use result, number of elements of order D in Zn will be phi D when D divides n. Otherwise we can't do this. So we have to find 15 as LCM. So first case is whenever LCM is 15 of 5 comma 3. So how we can find? So 15, so order 5 elements will be 5 5 into order of an element of order 3 r will be phi 3. Actually these are prime, so 4 into 3, because of if n is prime, then value of this phi n is n minus 1. So this will be 2. So 4 2 is 8. So number of elements may be 8. So these are few, and another one we can find 515 into 51. Value of 515 can be find out 1 minus 1 upon 3 and 1 minus 1 upon 5. So using this we can find out that, and value of 51 is 1. So 15 into 2 by 3 into 4 by 5. So this is cancel out. Again we have 8, and value of this one as LCM is 15 comma 5 will be 515 into 5 is same as 515, value is 8, and 5 is 4. So this is 32. So total elements of order 15 are 32 plus 8 plus 8. There are 48 elements having order 15 in Z60 into Z50. Remember one point, anyhow we have to form order 15 of elements which are coming from respective groups. So answer is 48.